Hello, everybody, and welcome to Week 8, Module 8. This week we're going to be talking about statistics and some specific statistical tests that we can use in research and inside organizations. Now, I'll say at the beginning of this that this is not the most exciting presentation. It's not the most interactive, obviously, that kind of stuff. This particular module is a bit boring, but I will try to get through everything. The good thing is that you can always come back and review this again and again and again. So if you need to leave and come back, that's perfectly okay. So again, just as a quick review from last week, we discussed independent versus dependent variables and how changes in the independent variable affect changes in the dependent variable. We talked about the difference between categorical, continuous, and ordinal variables. We talked about how survey research is the most common form of quantitative research inside organizations because it's the most feasible and easiest to do. But we also talked about some limitations of surveys and how they have inherent flaws in them as well. So this week we're going to be talking about very specific statistical tests. And I've categorized these into these five buckets, so to speak. So for each one, we'll talk about at least one kind of statistical test that can be used to do that certain thing. So for example, we'll talk about how to describe things. We'll talk about comparisons, associations, predictions, and explanations. So we'll go through each of these five, and we'll talk about specific statistics that can be used in each of these five categories. Now, the thing to note is that I won't be going into detail on equations on how to formulate or calculate these different statistics because most of the time these are done with computer programs anyway, right? You can figure these out in Excel or SPSS or SAS or different kinds of computer programs. So I'm not going to go into a lot of the detail on how to calculate them. For those of you who are more math-minded and it makes sense to you to look these things up, then I would encourage you to do that and look at the equations. But for my purposes, I'm simply going to keep it kind of at the surface level and talk about what they do. Okay? So, again, we'll be talking about these five areas. We will also discuss the meaning of univariate, bivariate, and multivariate analysis. So we'll get to that as well. Actually, as a matter of fact, let me just describe that to you now as a setting the stage for what we will go to next. So as you can probably guess, it's pretty straightforward. Univariate deals with one statistic, one variable. Bivariate deals with two variables, and multivariate deals with multiple variables. Okay, so we'll get to this a little bit later on, and you'll see how different situations, different statistics can be either bivariate or multivariate, and in some cases univariate as well. So let's first talk about statistics that describe things. So the most common statistics that we use to describe a sample or a population include these things, and these are things that you have definitely come across before. We talk about mean, median, mode, standard deviation, and frequencies. And I'll show you obviously the definition in just a moment, but I wanted to point out that the first four, mean, median, mode, and standard deviation, are often also called measures of central tendency. Now I'll show you a little bit later why that is and why we ascribe them to this idea of being centered or you know how spread out a data set is and things like that. Okay, so first of all, mean obviously is the average of a range of numbers. Pretty easy to figure out. You all have come across averages before many times. Median is simply the middle number in an ordered range. So think of like the median in a highway, right? It goes right down the middle. So the same thing is for a median in statistics. We're looking for the number that goes right down the middle. But remember, it's got to be in an ordered range. Mode is the most frequent number in the range, and you can also have if you have more than one mode, you might have a bimodal distribution or a multimodal distribution, right? So you can have more than one mode for sure. Standard deviation is the average distance from the mean. So if you look at the mean, if you look at the average of a range of numbers, and you calculate the distance from the mean to each data point you have, and then you take the average of that distance, you get the standard deviation. What standard deviation can help you understand is how distributed, how spread out your data set tends to be. Lastly, we also talk about frequencies. These are very simply known as counts of something, or and usually are presented as percentages. So those are frequencies. Pretty straightforward kind of stuff here. Let me show you just one thing that's connected to this idea of central tendency. Again, mean, median, mode, standard deviation are thought of as measures of central tendency. Many of you have seen this before, the normal distribution. And I just wanted to point out a couple things here. That if you notice, this is a normal distribution, or a bell curve, as it's also known. So you'll see here that there's lots of data. We're not going to go into all of this stuff. We're not going to go into each one of these numbers, okay? But I do want to point out one thing. If you look at the middle line in this table, it's labeled as 0. Okay, so if you look at where it says standard deviations over to the left-hand side, you'll see -4 standard deviations, -3, -2, -1, 0, and then +1, +2, +3, +4, right? That would tell you how many standard deviations are where your data set falls, or I'm sorry, where your data point falls, right? So if your data point falls +1 standard deviation away from the mean, right, above 1 standard deviation away from the mean, you know that it's really only it's a very rare kind of thing, right? And I say that because if you look right above that, you'll see percentages, 13.59%. Right? That indicates to you that only about 14% of your data points are are between 1 standard deviation and 2 standard deviations away from your mean. All right. So now what does that tell you? So it may sound confusing, but what does it tell you? It tells you that in a normal distribution, normally distributed bell-shaped curve, that most of your data points fall within 1 standard deviation of the mean. So if you look again, 34.13% to the right of the mean, 34.13% to the left of the mean, that's about 68%. So almost 70% of all of your data points are going to be very, very, very close to your mean in a normal bell-shaped curve, a normal distribution. Okay? Now, how do you interpret standard deviation? If you have high standard deviation, that means your data are going to be more spread out. And in this case, the normal distribution would not be normal anymore, right? It would flatten. So the peak would become lower and the edges would become higher. It would flatten out for high standard deviations. For low standard deviations, the opposite occurs. The peak in the middle becomes higher and the edges become more compressed. They go more towards the bottom, towards 0. Okay? So that's standard deviation. So again, if we go back and look, we could say, well, mean tells us one thing. Mean will say one thing. But if we can look a little bit further and find out standard deviation, we can find out how spread out the data points are. So as an example, if I were to compare test scores between my Wednesday night class and my Thursday night class, let's say theoretically that the mean came out to be the exact same. Okay, so the mean is the same for both classes. What could I do then? I could look at the standard deviation and say, all right, which standard deviation is higher? The class with the higher standard deviation would indicate to me that although the mean is the same, the scores were spread out, right? So I had more lower scores and more higher scores, whereas if I have a small standard deviation, I have scores that tend to be close to the mean. So I hope that helps you sort of visualize what a standard deviation is. It's telling you how, on average, how far each data point is away from your mean score. Okay, so standard deviation is an important statistic to hang on to. So let's go to statistics that compare. So using statistical measures, we're generally interested in comparing groups of people. So for example, men versus women, part-time versus full-time employees, officers versus enlisted, employees in Department A versus in Department B versus in Department C. So again, we want to compare these. Now, it could be comparisons on anything, right? Productivity, employee engagement, satisfaction, doesn't matter, right? What we're interested in is knowing, are there differences between these groups? So the first way we can compare groups is using what's called a t-test. A t-test compares two sample groups by telling us if they could theoretically have come from the same distribution. So again, hang on to this main point here. T-test is for two sample groups. If, on the other hand, we're interested in knowing more than two groups, we would use what's called ANOVA, or analysis of variance. So what ANOVA does is it compares more than two sample groups to see if they are statistically similar. So as an example, if we wanted to compare, look in our organization and look at the rates of promotion, men versus women, we could use a t-test. If, on the other hand, we were wanting to know the rates of promotion for our finance department versus our marketing department versus our logistics department, we would use ANOVA because we have more than two groups. So those are statistics that compare. We're looking at, are there statistical differences between different groups of people? Now, could you also theoretically do this? Could you also look at percentages between each group? So, for example, you could say men in the organization are promoted 62% of the time, women are promoted 78% of the time, and compare and say, well, it looks as though women are promoted more often. Yes, but that's not as robust as doing a t-test. A t-test will tell you if there is a statistically significant difference between the two groups. So a t-test is preferred if you're wanting to do a comparison. Let's now talk about statistics that associate. When we want to know the relationship between two or more variables, we use what's called correlations. And many of you have talked about correlations in your paper so far. You'll use the word even, correlations. So this might be something to think about when you think about your methods. If you've talked about correlations in your problem statement, you probably need to understand that you would be doing correlations in your methodology, your part 3. Okay? A correlation, the fancy pants phrase for a correlation is Pearson product moment correlation coefficient. So if you want to impress your friends, use that, the Pearson product moment correlation coefficient. What it does is it describes the linear relationship between two variables. The resulting statistic is a number between -1 and +1, and it tells us two things. So it tells us how strong is the relationship. So as it gets closer to 1 or -1, it's a strong relationship. If it's close to 0, it's a weak relationship. And it also tells us, is the relationship positive or negative? So positive would indicate that the two variables move up together or down together. A negative relationship would mean that they move in opposite directions. So let me give you some examples. So you see here that I've put some examples up here. What you have to imagine is that every data point you have is plotted on two charts. So let's say, for example, on the right-hand side of the screen, you see exam results and you see hours revising. So you have two data points for every single individual. So you know what they scored on a test and how many hours they spent revising. You plot that on an XY axis. Okay, that's essentially what a correlation does, is it plots all of these data points on an XY axis. And you then see if there's a relationship between them, if there's a linear relationship. So the slope of a line, if you remember from high school algebra, you look for the slope of a line. Now what I want to point out is that the statistical numbers that I've provided here are guesses. They're not perfect. I just sort of made these up based on what you see on the screen. So if you look at the left-hand side of the screen, you see degree of correlation. You see a strong positive relationship. What do you notice about the dots in that box? You should notice two things. One, that they're moving up together, okay, and that the dots are close together so that they almost start to form a line themselves. So again, they're moving in the same direction. As you go up on the x-axis, you also go up on the y-axis, okay? For a weak positive relationship, the one just below it, you have dots that are sort of moving in a trend line, right? But they're not as close together. So notice to the left you see an R value. That's the Pearson product moment correlation coefficient. R might equal 0.5. So you'll notice that it's not very close to 1, but it's still positive, right? They're still both moving in the same direction. Both, when one moves up, the other moves up, okay? And in the last example, on the far left-hand side of the screen, you have no correlation, right? All of the dots are sort of spread out. Same idea in the right-hand column. You have strong negative relationship where as one variable moves up, the other one moves down. Okay, so that's a negative relationship. As one variable moves up, the other one moves down. So moving in opposite directions. Okay, so that would be a negative correlation. Again, you'll notice that the dots, as they are closer together, the number gets closer to -1. So in this example, R equals -0.8. In the one below, a moderate negative correlation, R equals -0.7. And again, I'm making these up just to illustrate. And then a weak negative correlation might be R equals -0.5. So those are correlations. Again, that R value tells you two things, and that's the most important thing to remember. One, the direction of the relationship, and two, the strength of that relationship. Let's now talk about statistics that predict things. So if we're interested in knowing an unknown variable, we can use what's called regression analysis, or multiple regression if we have more than one independent variable. So let's take an example. If we knew that there was a relationship between your fitness level, your weight, your age, and your gender, just as examples, and the time it takes you to complete a marathon, we can use a regression analysis to predict the dependent variable, which is time to complete, based on known or estimated independent variables. So if we knew that there was a relationship there, we could say fitness level plus weight plus age plus gender predicts the time it might take you to complete a marathon within a given range of acceptability. So that's basically what a regression analysis would do. Now, if you think about it, what we're doing is we are extending a trend line, right? We're saying, given known variables, can I predict an unknown variable? So think back to regression and correlation. Essentially, we're extending these trend lines and saying, given this known variable, how do I predict this unknown variable? So regression analysis is based heavily on these correlation analysis and how each of these variables are correlating to the dependent variables. Okay, so again, basic takeaway from this is that we're predicting an unknown variable from variables that we already know or that we can estimate, right? So if we can estimate your fitness level, your weight, if we can estimate your age or your gender, we can then use that to predict the time it will take you. Okay? Now, that could deviate, and that's called error. So if it deviates from what the prediction should be, so let's say we put all this stuff in and we predicted that it would take you 6.5 hours to complete a marathon, and you actually completed in 6 hours, right? Then that's called error. We were a little bit wrong on that, and that's called error. Remember that a prediction and regression analysis does not imply causality. So same thing with correlation. We cannot imply causality. We cannot assume that just because we know your fitness level, weight, age, and gender, that it is causal of the time that it takes to complete a marathon. So we just have to be careful of that. Lastly, we talk about statistics that explain things. So explaining outcomes is a bit more related to the research design rather than the statistic itself. To explain something or show causality, we can still employ some of the statistics already described, so for example t-tests and regression analyses and correlations, but it needs to be in an experimental setting. And experiments are the gold standard of research, but they're difficult to carry out in real-world settings. So why do you think that might be? Well, some reasons are because of ethics reasons. It could be because you don't have access to certain individuals, because it takes a lot of time, because it's difficult to get it right. All of these things can add up to being pretty difficult to carry out experimental research, especially in real-world settings, so especially in organizations. But let's talk about this a little bit further. In an experimental design, you're interested in comparing at least two groups of people. And I say at least because you might compare more, but at least two groups of people. So in group one, they don't get an intervention. So maybe it's a training program, maybe it's a new mentoring program or a coaching program, but they don't get that, and that's called the control group. Group number two, the experimental group, they do get the intervention. So you do send them through the training, you do give them coaching, you do give them access to a mentor, right? And then you can test the differences. How would you test the differences? Well, you could use a t-test. If you had more than one group, you could use an ANOVA. So again, the difference is simply in the design, the setup of the study that we're doing. A truly experimental design relies on random selection of probabilistically similar individuals into the two groups. So we want to make sure that the individuals that are in the groups themselves are very, very, very similar to each other, so that we can weed out any of the other influences that might be happening, any other external influences. Can we always do that perfectly? Absolutely not, right? Because people have all kinds of characteristics that might lend themselves to a certain outcome. We have to be really careful about that. But experimental design can help us then to predict and say, okay, because these folks got this mentoring program, because they got this training program, I can then predict that the outcome was higher productivity or lower productivity or whatever the outcome variable that you're looking at. Okay. Now, for us, often what we do is quasi-experimental. So quasi-experimental, you still have a control group, you still have an experimental group, but you're probably not using random assignment, right? You're not saying, all right, let's take these 50 people, randomly distribute them into two groups of 25 each. The first group of 25 doesn't get the intervention, doesn't get the training program that we've designed, but the second group does. Instead, what you might say is, you know what, let's just pick 25 people as a convenience sample. We'll give them the training. We won't give the rest of the organization the training, and we'll see. That's called quasi-experimental because it's not quite up to the standard that we want it to be, although it's a very good standard to have. So, in sum, I've covered a lot in this module. Here are your key takeaways. In order to describe things, you use measures of central tendency, mean, median, mode, standard deviation, frequencies. To compare groups, you would use a t-test for two groups. You would use ANOVA for more than two groups. To associate variables to each other, you use correlation coefficient. To predict something, to predict an outcome, you use what's called linear regression or multiple regression. And finally, to explain things, you use an experimental design. Remember that the experimental design is really the only research design that is credibly able to show causality, and that's important. A correlation cannot show causality. You cannot imply causality. When you're comparing, when you're saying this group is different from this group using a t-test, unless that's an experimental design, you cannot infer causality. If you're predicting something using linear regression, you cannot infer causality. Remember, it's the experimental design that can show causality. All right. Finally, we just have some reminders. Complete your quantitative quiz. Remember that you can use your notes, you can use your book, all of that great stuff to complete your quiz. Remember to read Swanson and Holton chapter 13, and then next time, our next module, will start on qualitative research. All of this should build into your chapter, your part 3, your methodology. And of course, if you have any questions whatsoever, please feel free to reach out.